Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be another of my Tactica Tutorialis science lesson videos, and today we're going to be doing a GCSE science and physics topic, that being heat, or more particularly specific heat capacity is going to be our topic for today. The learning objective, if you're one to write those sorts of things down, is to define and calculate specific heat capacity, or SHC. We're going to do that both theoretically and we're going to have a practical as well, which you can also have a go at home to get yourself some practice at doing this sort of thing. So we've got a few things to cover today. I want to talk about heat as an energy store in and of itself and separate that from temperature, because there's a common misconception that they're the same thing. Then we're going to get into what SHC is as part of its derivation, and then we're going to do some calculations with it before we get into the practical. And this is something that you would normally do at school. Certainly on the current GCSE specification that I'm teaching, they mandate a SHC practical. It's what's known as a required practical on the specification. So getting some practice at this, even if you're not currently sitting this sort of exam, either because you don't have to or your spec doesn't do it, it's good practice for practical work anyway. So, as I say, we have plenty to do and plenty to dive into. All the solutions for any exercises we do can be found at the top of the description when I ask you to do them. But without further ado, class is in session. Let's begin. So, to start us off for today, let's have a talk about energy and temperature, because we're going to be talking about heat as an energy store today, and a lot of people get a bit of a misconception about what heat energy is and what temperature is, and many people conflate the two and think that they're the same thing, but they're not quite the same thing, and we're going to attempt to explain that as part of this opening segment. So, first off, I would like to pose a little thought experiment question for you. So, imagine, if you will, that you had a nice cup of tea. Yes, I know this is empty. I don't make tea. I gave away all my tea bags when we started quarantine. So you have a nice cup of tea, and you have an iceberg. A big one. A really big one. Like you'd find up in the north, up in the Arctic Sea, or down the Southern Ocean near to Antarctica. You've got a big old iceberg, and you've got your nice cup of tea. Of the two, which of them is the hottest? And of the two, which of them has the most heat energy, or the most energy within what we call its thermal or heat store? So, two questions for you to answer, and I'd like you to take about 2 or 3 minutes to think about it. If you're doing this with someone else, then feel free to discuss it. If you're watching this live, discuss it in the chat. But what do you think? Which of the two is hottest, and which has the most energy stored in its thermal store? Now, I'm not going to put solutions in the description for this one. I want everyone to hear it. It's a very important point. So pause the video, answer the question, 2 to 3 minutes, off you go. So, answers then, now that you've had some time to think and have the video on pause. So, of the two, which is going to be the hottest? Well, the answer to that one hopefully was relatively intuitive. It's going to be your nice cup of tea. I would hesitate to say how hot a cup of tea is, but typically, because you put boiling water in it, a cup of tea is very, very hot. Probably after you've added the milk, it's probably somewhere in the 90s, maybe in the 80s of degrees Celsius, whereas an iceberg is made of ice, and ice would melt above a temperature of 0 degrees C. So, in terms of temperature, the tea is much hotter. Therefore, tea has higher temperature. But what about the energy stored within the cup of tea and the iceberg? Which of them has more? Well, you might be surprised, but it's the iceberg. A cup of tea is hot. Yes, it is. But a cup of tea is very small. There's not a lot of tea in your cup of tea. Whereas an iceberg is huge. And heat energy is not equal to the temperature of the substance. It's made up of a lot more things that we'll meet later in the lesson. So it means that because the iceberg is bigger, and actually in this case, because it's made of water, pure water, hopefully, or maybe salt water, depending on what your iceberg freezes into, it's got a lot more energy stored within it, even though it is much colder. It's more energy. And that's a very important distinction, because it can be very easy to look at two objects and say which one's got the most energy, which one's got the most heat energy. Well, this one, because it's hotter. But it can be that the colder substance has got more energy stored in its thermal store because of different properties. And that's what we'll get to in a moment. But I'd like to give you one definition that I'd like you to take down before we move on, so that you can see a bit more clearly the difference. And that is what you'd call the definition of temperature. So define temperature. I write def sometimes in shorthand, DEF, for define, because I did coding when I was at university, and that's the shorthand for coding. So temperature is defined as the average kinetic energy of the particles in a substance. And that really should say all the particles in a substance. So notice that I'm talking about kinetic energy, which we did a lesson on a good number of weeks ago, if you want to go and cast your mind back. So in a substance, you have particles pretty much always. But the only thing I can think of that doesn't have particles is light, and even then we're getting technical with that. Not getting into that today. So these particles move, they vibrate, they're able to flow, they bounce around, depending on exactly what state of matter your substance is in. And that means that they have kinetic energy because they're moving. Now, when you heat something up, we haven't talked about this on the channel, but we probably would have met this on our specifications in different places. If you heat a substance up, those particles move more. So they have more kinetic energy. And if you were to take an average across the billions and billions of particles that most substances are made of, and took an average for their kinetic energy somehow, you would arrive at the temperature. So if you took all 5 million particles, added up their kinetic energies, divided by that, the number you had, took a mean, that would be the temperature. It's not measured in units of energy, it's measured in a few different things. So typically you'll find it in degrees C, or you might find it, if you're particularly American, you might find it in degrees Fahrenheit. And at higher level science, and I'll try and use it in this video as well, you will also find it in what we call Kelvin. That's the sort of universal scale. These are sort of more manageable, readable scales. This one is the one that has absolute zero on it. So that is the definition of temperature, and I'd like you to take that down. So with that done, now you've got a better idea between heat energy and temperature. Let's get into some mathematics. Let's get into what heat energy is, actually get some maths behind it, and derive specific heat capacity. All right then, the heat equation. This is one of those equations that at GCSE, which is obviously what we're doing today, comes up a lot and ends up causing a lot of consternation for many students. So it is a good equation to get to learn by rote. Technically, you don't need to know it by rote at the time of recording this video. It is not a one you have to know by memory. It is given to you either in your test or on the formula sheet. However, actually being able to manipulate it is a different kettle of fish, so I would definitely be getting the practice. So, the heat energy goes as follows. So, E equals mc and then your terminology will vary. The way I personally write it, and the way I've seen it written at schools I've worked at, is delta theta. Now, I'll define what those mean in a second. So that means that if we were to create a formula triangle, we would arrive at something like this. E, and we break it up into 3 sections at the bottom, M, C, delta theta. You might be wondering why there's 2 symbols in there. Again, we'll get to that. So let's define what all of this means. What does EMC theta mean? Well, E is equal to the heat, or you could say the heat energy. So the unit for it is going to be the same unit that energy always has at GCSE, and that is going to be joules. In fact, it's the unit that energy has no matter how old you get. M is a very common symbol. You've seen it before, more than likely. That is the mass of the substance. And that is measured, as we've said in other videos, in kilograms. I know you might think, why not grams or something like that? It's measured in kilograms. Delta theta is equal to the change in temperature, which, at least as far as we see it at GCSE, is in degrees Celsius. We don't get into Fahrenheit and Kelvin particularly. You may get into Fahrenheit depending on your specification or Kelvin, but at least on the spec I teach, that is in degrees Celsius all the time. Now you might be wondering, what's this triangle doing here and what's this weird circle with a line through it? Well, it's a very common notation to use a delta to symbolize a change in something. You'd see it actually a lot if you got to higher levels of physics and maths, I think, as well. Delta typically represents the change in something, and whatever it is in front of means the change in that parameter. In this case, theta, the temperature. Now you might be also saying, Tactica, why are you using this random circle with a line through it? What's wrong with a capital T? Well, honestly, I can't tell you. I didn't make this up. This is not my design. I think the main reason we use theta instead of T is to prevent people getting confused with time. Now, I know theta is used for angles, which is why I like having the delta with it as well. So delta theta for the change in temperature. If you would prefer, you can get rid of the delta, or you could change the theta to a T. Your specification will guide you on what symbol you should be using in your own exams. But for the purpose of this video and the specification that I have used, we use delta theta for the change in temperature. And that leaves us then with C. Now C is defined as the specific, that is how you spell it, heat capacity. And if you were able to work it out, you would get its unit, which I'm going to give you because it will take a while to get it, as joules per kilogram degree Celsius. Because, well, I won't tell you the because, I'm going to set your first little task. So what I'd like you to do, give yourself about a minute, maybe 2 if you feel a little bit less confident with your equations. I would like you to rearrange this equation and solve it for C. So get it into a form of C equals, because you will use C equals something quite a lot throughout your calculations with this formula. So it would be good to get it written in your notes. So have a go for about a minute or 2. Have a go at getting C equals. What do you think it is? Give yourself a minute, pause the video. Okay, so you've hopefully had a chance to pause the video and have a go. So if we're trying to get C on its own, the first thing we could do is call to our formula triangle. Remember how this works is we cover over the parameter that we're trying to work out, and it tells us what to do in terms of the formula. So if I was to cover up C, for a moment, that tells me I've got to do E divided by M and divided by delta theta. So I do E divided by M delta theta. Because if you think about it, it's each of these is a little, oh, the pen, this lid's stiff. It's a little multiplication. M times C times delta theta. So if I cover up C, I'm doing M times delta theta. So you might write it another way is like this, M delta theta, if that more appeals to your sensibilities. So get that formula written down alongside this one, as well as the definition of all of these symbols. I'm just going to tidy up my pen work because I think my jacket slightly brushed the page. Give me a second. There we go. So those are your definitions, those are your symbols and what they mean for the heat equation. When you've got that down, I'm going to give you a closer definition of specific heat capacity. Alright, so a moment ago I introduced this idea of something called specific heat capacity, which is a thing, and it's a very important thing to define in terms of a substance. Every material has a specific heat capacity, or for short, SHC. You'll get used to writing that because I'm not writing this 1700 times. So the SHC of a substance tells us a lot about that material, and we'll address this a little bit more as the lesson goes on. But first, let's get the core information, a little fact file on the thing, if we shall. So the first off is the symbol that we use for it in equations, and that, of course, is a lowercase c. Not a capital C, a lowercase c. Other hand, not capital, lowercase c. In terms of the heat equation, well, we already just did it. You all have done it for yourselves. C is equal to E over M delta theta. Or you might prefer E over bracket M delta theta. They do mean the same thing. Personally, I prefer this look because of just the neatness of it. M delta theta. There we go. I prefer that because I think it's neater, but that is also fine. In terms of its unit, I gave it to you as joules per kilogram degrees Celsius, or if you prefer to write in power notation, it would be joules, kilograms to the -1, degrees Celsius to the -1. If that's your preference, again, this is the one you'll probably see. And the reason for that comes from this. So if you were to plug the units of the heat equation in, you would find, of course, energy has a unit of joules, hence the joules on top, and we are dividing by a mass, hence the kilograms, and a temperature change, hence the degrees Celsius. So we are doing joules divided by kilograms times degrees Celsius, therefore joules per kilogram degrees Celsius. If you can work it out, it actually makes it easier than remembering it by rote. So I would say that if you can work this out and remember the units of it, you'll be able to remember this by sort of process of elimination. Rather than trying to remember them both independently, I would suggest you learn this and the units of these to help you remember the units of this. It's up to you, though, in terms of how you do it. As for a definition, this is the bit that absolutely must go in your notes. I'm not taking any ifs, buts, or coconuts. So, the definition of SHC is the energy required to raise the temperature, actually raise or lower the temperature of 1 kg of a substance by 1 degrees Celsius. Now that's very long-winded and probably looks like a giant pile of word salad. So let's break it down. So we have 1 kilogram's worth of stuff.
this stuff can be made of whatever we want, and we want to heat it up or possibly cool it down. So how much energy am I going to have to put in to heat it up? Well, if I want to raise the temperature by 1 degree C, I have to put in a certain amount of energy. And for that, I need to put the amount of energy equal to the specific heat capacity. So if I had, as I say that one more time, if I had 1 kg of stuff and I heated it up by 1 degree Celsius, the amount of energy I have used or put in to do that is equal to the specific heat capacity. It is the energy per kilogram per degree Celsius of temperature change. And that is why this unit adds up and why this equation adds up. They all fit together and they all say the same thing. This says it in words, this says it in symbols, and this says it in mathematical and physical units. They all say the same thing. I would absolutely mandate that you put, let me just get another coloured pen. Yeah, I found I had a drawer in the side of my little pop-up desk, so I'm going to use it for this. I'm going to mandate that this go in your notes. No arguments. That definition goes in your notes, and I would also suggest you pop this stuff in your notes just as a good helpful reminder. As I said, you will be given E equals MC, whatever your symbol for change of temperature is, on a formula sheet. You will not be given this, and you will maybe not be given this. So it's a good habit to have them in your notes. Anyway, once you've taken that down, coming up on screen is going to be a series of calculations all about the heat equation and specific heat capacity. There's going to be 4 of them. So there's a little bit more than we typically do to give you some good practice at using these ideas. There's also going to be an extension question. Now, I would ask that you answer that extension question, but the solutions in the description will not answer them because I want to talk about it at the end of the lesson. So, have a go at all 5 of the questions that are going to come up. The solutions to the 4 calculations will be linked at the top of the description under the subheading Calculations Solutions. So go click that link when you've had a go. I say you give yourself around about 10 minutes, no more than 10 minutes to have a go at those 4 or 5 questions. And if you can get the extension done, then all the better. We'll talk about it at the end of the video. Once we've done this, and you've done that, the next thing we're going to do is our little practical demonstration. So the running order for now. Pause the video, take these notes. Next section, calculations. Do the questions, write them in your notes, get an answer, take the top link in the description in order to get the solutions to those answers. Then unpause the video again, and we'll go on into the practical before we have our final discussion, which is going to be all about insulation. So 10 minutes to get this. Once you've got this down, 10 minutes to do the calculations. Good luck. Off you go.
So we've now arrived at the practical portion of today's lesson. Now I'm not going to run through and actually do the full practical here because it's quite long, it's quite loud, and to be honest, it won't serve as much of a benefit as you might think. But up on the screen, I'm going to put them up in that corner. I'm going to leave a method and an equipment list for the practical, and it will then appear on the screen after I finish speaking so that you know what you're doing. So if I'm off to one side, that's because there's some text coming up in that corner. So the equipment you are going to need for today's lesson. You've got 2 that you do need and 1 optional extra. The first thing you will need is a way to tell the time and keep time. So a watch will do at a minimum. If you have a stop clock or a timer on your phone, that will probably do even better. The second piece of equipment you're going to need is one of these. This is a kettle, which I'm sure most of you know, and ideally you want a kettle that comes with a power rating on it. So this one here says that it is 2,520 to 3,000 watts. I'll let you pick the number you want to be your power. If you've got a range like that, I'm going to go with the upper number of 3,000 watts. And that is very important because we need to work out the energy involved in our practical. So we have the kettle with its power rating, we have our timekeeping implement, and optionally you may also wish to have, if you have one in your house, a thermometer. You don't need one, there is a workaround, but if you have a thermometer, it will speed your experiment up. So what you're going to want to do is fill the kettle with 1 litre of water, because water has a density of 1 kilogram per litre. That's not its density in SI units of 1,000 kilograms per meter cubed, but per litre, water has a mass of 1 kilogram. And if I look at my kettle, this can hold 1.7 litres, so your standard kettle can probably hold a litre of water quite easily. Before you put the water in though, you probably want to know its temperature. Now, you can do this with the thermometer, obviously, if you have a thermometer on hand, but even if you don't, you can cheat your way to getting a suitable answer. The 2 methods I would encourage is either stick it in the fridge, at which point it will reach the temperature that your fridge is at, which is probably 3 to 5 degrees, depending on the quality of your fridge. Or if you have a thermometer on your wall that tells you about the room temperature, then you can use that and leave your water next to the thermometer or in the same room so that it will eventually, if you leave it for an hour or 2, reach that temperature. Essentially, you need to get your water to a temperature that you can know, either because you've measured it or because you've left it long enough that it's reached what we call thermal equilibrium and is the same temperature as a place where you do know the temperature. The fridge, the room, whatever it so happens to be. And when you know that, you put your water, 1 kilogram, into the kettle and you're going to boil that water. So you'll turn everything on, and when you hit the switch to click go to start your kettle boiling, you're also then going to start counting on your timer. So if you've got one hand on your phone, one hand on the kettle, 3, 2, 1, go. And you'll press both at the same time, and you will time how long it takes for the water in the kettle to boil. Typically, the best way to do that is wait for the kettle to turn off, is probably your best measuring point, because you can't leave a thermometer in your kettle. That's probably just an all-round terrible idea. So we're going to work to the time at which the kettle stops boiling and all the water has reached boiling point, which, as many of you will know, is 100 degrees Celsius. At that point, we know everything we need to work out the specific heat capacity of our water, which is the practical that we are doing. I forgot to mention that earlier. We're working out the specific heat capacity of water. And with the information we now have, we can actually do that. If I get my pen, I will go onto my whiteboard and I will show you exactly how we go about doing that. So, the things that we now know about our experiment that we've either read off or we've measured or we've counted. We know the power of our kettle. That should be on the sticker if you've got it. And we know the time it took for the kettle to boil. Those are 2 things that we know. And you may know this already from the energy topic. If we bring those 2 together, we arrive at a formula that says that energy is equal to power multiplied by time. E equals P times T. It's a formula you might have met before, but you definitely meet it throughout this topic. Which means if we take the power of our kettle and multiply it by the time taken for it to boil, we can work out the energy transferred by the kettle during the boiling process. We also know the mass of our water because we put 1 litre in, therefore we know our mass is 1 kilogram. And finally, we need to know our temperature change, that delta theta that we've seen already. And for that, we already know that water boils at 100 degrees Celsius, because that's a very well-known fact, and you can look it up if you don't believe me. And you will have measured the starting temperature of your water. Either because you left it in the fridge, you used your thermometer, whatever you did, you will know what temperature your water was at when you put it in the kettle. Therefore, if you do 100, take away that, you arrive at your delta theta. So now we know energy, we know mass, and we know the change in temperature, which leaves us one task: to calculate the specific heat capacity of the water. Because we're going to assume that all the energy transferred by the kettle went into heating the water, which is not strictly true. Efficiency says no, and other energy stores such as like lighting up the kettle and all that says no, but we have to assume efficiency unless you happen to know how efficient your kettle is. So if we stick that in, we know that from the formula that we've used earlier, specific heat capacity C is equal to E over m delta theta. That is the formula that we've used throughout the lesson. You've used it a few times up to now. And if we stick in the energy we worked out, the mass that we know, and the temperature change that we calculated from our data, we should be able to get a value for the specific heat capacity of our water. And that's it, actually. But you might be interested to know, what sort of number should I be aiming for? Well, I think this might have been in one of the questions. I'd have to go and double check. But the specific heat capacity of water is 4,200 joules per kilogram degrees Celsius. Roughly. Your mileage will vary depending on exactly how pure your water is. So if you have a number between 4,000 and probably 5,000 for your specific heat capacity, you're probably on the right lines. I would not be surprised to find that your number is a bit too high because of the fact that your kettle is not 100% efficient, and you also don't know the overall temperature of the entire bowl of water, because some of it will be hotter than other areas due to the fact that some of it's boiled away to steam and evaporated, leaving just colder water behind. It's not an exact science, but it should give you an idea of the methods that you're using, and you can absolutely repeat this practical a couple of times and get yourself an average by taking a mean to get yourself a better value for the SHC of water. So that is our practical. If you want to have a go at it, I will leave a set of instructions and the equipment that you will require on the screen to remind you what I've said over the past few minutes. And once you're happy, if you've had a go at it yourself, let me know what number you get in the comments. I'll be interested to see what you get. We're going to wrap up by talking about the extension question from the activity that you did before where you were answering the calculations. I want to talk about that in more depth to wrap up for today. So, here we are at the end of the lesson. This is going to be our final activity for today, now that we've seen how to do specific heat capacity mathematically and experimentally. And what we're going to do is the extension question from the questions that I set you earlier. Sorry about that. Pen lids are stiff. So in that extension question, which I didn't go through in the solutions video, I asked you to compare the specific heat capacities of two different materials in order to derive which one of them was the better insulator. Now, hopefully you've had a bit of a guess about that one if you've done it, but we're going to go through the answer to it now, which means I have to put a spoiler warning. If you are one of those people who likes to do the exercises, then please do it now. Go back, do it now, because I'm about to give away some of the answers. So go back, do it now, and then we'll discuss it. So, the two materials we had were some lead and we had some sandstone. And in the questions, we worked out that the lead had a specific heat capacity of 129 joules per kilogram degree C. And we worked out that the sandstone had a specific heat capacity of 710 joules per kilogram degrees C. So we worked those out in the solutions video. You can go and find the working in the solutions video if you have forgotten.
and we wanted to ask which was the better insulator. And in the question, I did give you a hint about how insulators work. Insulators do not cool down or heat up very quickly. And remember that if you want something to be insulated, you want it to hold its heat for as long as possible, to keep the heat in so that it doesn't cool down. But if you don't want it to cool down, you also therefore would be saying you don't want it to heat up very quickly. In fact, they kind of mean the same thing. So by an insulator, the hint was, therefore, doesn't heat or cool quickly. So if you are interested, even if you didn't go and do that exercise, I'd like you to have a think about this now and discuss it if you're with chat, or just think about it to yourself. Which of these two do you think is the better insulator? You know what the materials are, and you can see the specific heat capacities. Can we work it out? Give yourself about just 2 or 3 minutes to talk about it if you need to, and think about it, and then we'll talk about the answer. So it all comes down to this: the rate at which something heats up or cools down. And that is intrinsically tied to the specific heat capacity of the material. So if you think about it, if the material is cooling down, it's going to have to emit a certain amount of energy before its temperature is reduced. Because remember, they're tied together by E equals mc delta theta. And if we think about the definition of a specific heat capacity again, it is the energy required for 1 kilogram of a substance to change temperature by 1 degrees Celsius. And that means that 1 kg of lead will need to emit, I don't want to say energy is lost because that's the wrong word, 129 joules to cool 1 degree C. Whereas 1 kg of sandstone will need to emit 710 joules to cool 1 degree C. So if we look at that and we say, okay, so if I've got a kilogram of lead, after it has emitted 129 joules of heat energy, it's going to have cooled down a bit. And the energy emission, if you're at the same temperature with the surroundings, it's all like that, is going to be at a constant rate. So if they're both at the same temperature, then they're going to cool down at the same rate in terms of the energy emission. But the actual cooling, the change in temperature, will happen faster in the lead. The lead cools down faster because of its lower specific heat capacity, meaning it needs to emit less energy to cool down. So we therefore say that the sandstone is the better insulator because, now you could write a longer form answer here, but the real short of it is it has a higher specific heat capacity. The sandstone has a higher specific heat capacity, so it will take longer for it to cool down, or you could say heat up. So if you have, for example, a block of metal and a block of, well, stone in this case, and you leave them out in the sun, probably the metal block's going to get hotter because it's able to increase its temperature more when it receives the same amount of energy thanks to its lower specific heat capacity. And that also means when they're cooling down or emitting heat, the stone will take longer to cool down if they start at the same temperature because it has the higher specific heat capacity. Therefore, it is the standard insulator. And the opposite to an insulator is a conductor. And you may already know that metals are very good at conducting heat. This is why they're low SHC. So, that is the last thing I wanted to cover for today. make sure to add this solution into your notes and discuss this, and make sure that you've got an idea in your head about how insulators work, because whilst this is not a universal exam question, it's certainly a very good application question that could definitely get asked. So make sure you've got it in mind. And once that's done, we'll be at the end of the lesson. So thank you very much for all of your time, your hard work, and your effort in getting through this lesson and doing the exercises if you were doing that. If you have any thoughts or you have any requests for a future lesson, please do let me know via the comments section below. I'm always listening and reading the comments, and I like to do lessons based on requests as well as my own interests. Our next lesson, I think we're going to go back to some nuclear physics. I think I want to talk about nuclear fission for a lesson, and we will eventually get on to doing nuclear fusion as well. But of course, if you have any requests, I am more than open to that as well. So with that all said, class dismissed. Thank you for watching Tactica Imperialis, and this has been my Tactica Tutorialis lesson on specific heat capacity. I'll see you all again. Bye for now.